to start. I am recording now. I will post this video later on today or tomorrow morning at the latest in the content area of Brightspace. We have finished the material which would allow you to take the first quiz. We should have done that last week. So the first quiz is posted up on Brightspace. It's in the content area. You should be able to see it now. It's 10 questions. Most of the questions revolve around things that we actually discussed in class, but there's a couple of questions that I think will be a test to see if you understand the concepts of the ideas and thoughts that we discussed in class. So what I mean by that is there's a couple that you're going to have to really put your thinking caps on. Uh, and the rest of them are just uh, questions that revolve around things that we absolutely positively discussed in class. 10 o'clock next Friday, the quiz will um, close automatically, and that will be it. So I would hope that if in fact you can't see the quiz, that somebody would tell me before next Friday at 9:55 that they can't see the quiz. It's there. I'm pretty sure it's accurate, but there is technology, and sometimes it might not push the right button and activate the right visibility feature or something like that. So let me know if you have an issue with that. Sooner the better. And the best way to communicate is definitely through text message, not through email. I don't check my email, but I pretty much do see all my text messages right away when they come in. So that would be the best way to communicate at all times. And I don't want you to send me um, copies of your spreadsheet. I'm happy to go over your area calculations with you uh, in a Zoom meeting, a private Zoom meeting, or during office hours, which are on Mondays. I think no, I what's today? 27. Yeah. Okay, yeah. So we do have office hours next Monday, but I think the Monday after that I won't be able to have the office hours from 9 to 11 on Monday. But next week, definitely we can do that. So the reason I just don't want you to send me an image of your spreadsheet in your areas is because then how do I query you? How do I ask you questions? Are we going to go back and forth with emails for 15 or 20 repetitions of back and forth? How did you do this? Where did you get that? How this is not correct. It's too low. It's too high. So if we can just allocate a few minutes on Zoom, and I'm happy to do that outside of office hours or during office hours, then we can get that first phase of the project correct because as you hopefully recognize by now, every phase of this project sort of looks back at the previous information that you've entered into your spreadsheet. So if the previous information is incorrect, then everything is incorrect because it's the next state phase is based upon previous information, and the phase after that is based upon previous information. So it has to be correct. So I'm happy to go over that to make sure that you get a good start with accurate area calculations. If you're positive that your numbers are okay, then of course we don't have to review them, but I think it's a good idea. I think it's a very good idea for you to take advantage of um, my willingness and ability to look over your numbers and make sure that they're correct so that when you move on to the next phase, they're not wrong. So I've said that many times. I hope it's uh,
Yeah, I just wanted to ask, did you take attendance yet?
say it again.
Did you take attendance yet?
I have no idea what you said. I can't hear you. Let me turn my speakers up a little more, maybe. Nope, they're full volume. All right, so ask it again.
Asked if you took attendance.
I am working on that. Yeah. I started taking attendance. I just take a look at who's popped into the room. I started doing that before class even started. So no, I haven't finished taking attendance, but I have started doing it. Yes.
Okay.
I'll take it at the end of the class. That's the more appropriate place to do that. So anyway, then we'll get into I think we left off around somewhere around here. Last class we talked about the eh, the air chamber that allows the water to pressurize into the air rather than pressurize against the fittings in the piping system, which what that does is eventually causes a failure. You want to have that water hammer effect occur by compressing air rather than by pushing up against the connections in your fittings. And so then we have a fixture unit. That's an arbitrary number. And if I were to ask anyone what a fixture unit was, and you tried to define that to me and did not use the word arbitrary, you would be at a disadvantage because it is an arbitrary number. There is no, when we looked at uh, British thermal units or when we look at foot candles, we have a an equation that defines what that variable is. But a fixture unit is just a arbitrary number that's used to define the water flow conditions um, in both supply and in drainage. But it's not a mathematically defined number. Okay, so I just saw a question about the project in the chat. Um, and the question was, and I don't know, maybe everybody can see it or maybe it's just to me, but what should my next step if I've done the R values? Well, the next thing would be to, which means you're probably very far ahead. But the next thing would be to look online for uh, a terminal unit, a radiator, find a hot water terminal unit, search for that and add that into your project, and then calculate how many uh, BTUs that particular terminal unit will provide per linear foot. So, for example, if you found a manufacturer that sold a 3 foot long terminal unit and they said that that unit provides 1,500 BTUs, well, we want to know how many BTUs does 1 foot provide. So we would divide the total amount of BTUs that that unit puts out by the distance. In that case, it would be 3 feet. And then we would use our number of 500 BTUs per linear foot. And that would be what we want to calculate. That would be the next step in the project. That's pretty far along for sure, which is a good sign. Um, the terminal units that the manufacturers provide might not come in 1 foot increments, but we are going to assume that those radiators, that terminal unit, can be purchased in a 1 foot increment for purposes of the project. So once you know how many BTUs a linear foot of terminal unit will generate, and once you've put in the proper information for all the R values, your spreadsheet should calculate how many R values you need for the entire house. And then you divide that by the square footage of the house, and that will tell you how many BTUs you need per square foot in the house. And then you know how many square feet the room sizes are. And so then you simply multiply to figure out how many linear feet you need of terminal unit in each room. That's getting closer to the end of the project. So I'll just say the next step right now would be the finding a terminal unit that uses hot water to radiate the heat, find out what it is, what the value is per linear foot. Would be the next step. So then we're back into the slides again now. We have the fixture unit, which is just an arbitrary number, remember that, but we have different values that we add for that. So we use that for a bathtub. You can see that the fixture unit is 2. For something like a water closet, which is a toilet, fancy name for a toilet, we use a lot more water. So our fixture unit is 6, but it's not 6 gallons of water. It's not 6 ounces of water. It's an arbitrary number that just talks about the fixture units and the amount of water that we're assuming that these different, not the physical measurement of the amount of water, but an arbitrary unit of measurement that we've applied to these various items here. Now, when we progress into the project much farther into that, we're going to actually do a riser diagram, which again, we haven't seen or talked about, but we will. And this piece of this will be very important information, which I will load up onto Brightspace for you. But different items, different fixtures require different trap sizes and waste sizes to get the wastewater away. So when you put a bathtub in a facility, certainly in this project, you need a trap, and this is the minimum size that the trap can be, and the waste diameter. In other words, what's the minimum sized pipe that we can have coming from our bathtub to get the wastewater once you've taken your bath and you want to drain the tub? What's the minimum size of a pipe that you can have? And you can see that we're pretty much in the 2 to 3 range until we get to what? Well, here's a 4-incher. That is the toilet, the water closet. So those are the things, and you will use this information, this table, definitely for when you itemize and draw your riser diagram for this house. And we'll go over what a riser diagram is, and we'll in fact, let's look at it right now then. Here's a riser diagram. This is basically what we're going to do for this project. And basically, we break it up into several floors. We have a basement, and we have a first floor, and we have a second floor. On each floor, we have certain fixtures, sinks, water closets, lavatories. Again, that's a sink. And a tub. Water closet is a toilet. And each one of these devices has a drain, and it has a requirement for that pipe coming out of it. So the tub, we said, if we went back to there, we said the tub needs a minimum of a 2-inch diameter pipe. So in your project, right here, when you do your riser diagram, you're going to say 2-inch minimum drain. When we go back and look at the trap size, the minimum trap size is 1.5 inches. So you'll label the trap from the tub as the minimum size of 1.5 inches. We haven't even gone over what a trap is yet, so we will get to that. But this is what a riser diagram looks like. And I will expect you to do that riser diagram for the house plans that I have provided you with. But for now, we're just looking at fixture units. We'll eventually be concerned about the trap size and the waste size. That would go into the riser diagram. But for now, just recognize that a fixture unit is an arbitrary unit of water flow used to define water flow conditions. Either supply, we have to get the water to the fixture so that we can use that water, or the drainage, the return, to get that water away from the fixture. In our riser diagram, We only are concerned with the removal of or the return, the waistline, where you don't see any information here about what size pipe we're sending to the various fixtures. That's not required in this course. Just we're concerned about getting rid of the water after we've used it. We expect that the water will be correctly and properly delivered to the fixture in this class. In a real project, we would specify all of the pipe sizes, etc. But for this class, we're just worried about the riser diagram that gets the water away from your fixtures in your project. So this looks familiar, so I think we did talk about this, but if we're in the subway system, which I think is wonderful, you have the ability to see some of these things. And those long pipes, they do have pipe supports. You can look up in the ceiling and you can see that those pipes that are traveling the distance of the subway need to be supported from time to time, and they're placed at intervals, really based upon the pipe size, the material, what the weight of the inside is going to be. You know, water weighs about 7 pounds per gallon. That's probably the heaviest material that would flow through there is water. So, you know, based upon its ability to carry all of those loads would be how the supports are sized. But we recognize, and we talked about last time, that there are some examples where when things get warm, they expand, and when things get cold, they contract, and these pipes have to allow for that amount of movement to happen. We also talked about the water recirculation before, and that California example where the homeowner calculated his work and with the circulating system on and the circulating system off, he determined it cost him $800 in heating expense. That's energy expense, but he didn't have to leave his water turned on while he waited for that hot water to get from the tank all the way to his sink. And so he saved water, but he spent energy. And even though we talked about the cost of water in California being expensive, he did not, the example that I talked about, the YouTube video I saw, he didn't think that he saved $800 worth of water by not leaving the faucet run long enough to get that hot water to the system by having a circulation system. And we did talk about purification, testing the water we put, because we know that the pipe side in the inside of the pipe, when it's delivered to the job site, has bad things inside of it. If nothing more than just dust, it has dust, but it also probably has other things that it's accumulated throughout the whole process of fabrication of that pipe to storage of that pipe in a warehouse, transportation of the pipe from the fabricator to the warehouse, transportation of that pipe from the warehouse to the job site, and storage on the job site until it was actually installed. They all have the inside of the pipe exposed to bad actors, bad chemicals, bad things that we don't want in our water supply. So once we put the system all together, then what do? We purify it. We fill it up with chlorine for a period of time and let that chlorine disinfect the inside of the system. And then what do? We drain it. We flush clean water through that to get rid of the chlorine. And then we have a system that will actually work and deliver clean water, not water with any kind of contaminants in it, because those have all been flushed out. And then we also talked about the expansion, so it's a little bit of review here. But we recognize that pipe does expand as T2, which is the final temperature. If that's greater than T1, which means we're warming it up, then this number is going to be a higher number, which means that our formula is going to have a higher change in length than if it were cooling down. In other words, if T1, the final temperature was less than the initial temperature. T1 is the initial temperature, T2 is the final temperature. So if T2 was less than T1, then this would be a smaller number, which means, or a negative number actually. Could be, if T1 is warmer than T2, then that's going to be a negative number, which means that T2 is cooling down, which means what? This is going to be a shrinking number, or a smaller number, a negative. Okay. So we did the example of that. And so when we talk about the flow rate, what do we want? Well, we want the water to flow away from the source, the sink, the toilet, the tub, the shower, the dishwasher, the washing machine. We want it to flow away. And we want gravity, whenever it's possible, we want gravity to take that water away from the fixture to wherever we want that used water to end up. And we want that normally to be about 1/4 inch per foot. If you walk on the sidewalks outside of the school, campus, or really anywhere, the sidewalks generally slope about 1/4 inch per foot, which allows the rain to slope away. Any more than that, it's uncomfortable for us to walk on, but it allows the water, 1/4 inch per foot allows the water to slope away. And that's a good general rule of thumb. We can change that based upon the size of the pipe, but I don't think that that's a bad rule of thumb. Is to just say we're going to slope our pipes always at 1/4 inch per foot minimum. So for every horizontal foot of distance that we travel, the pipe will drop 1/4 of an inch. Again, if you look at a long distance of pipe travel, that's a substantial drop in the elevation of the pipe, and that can make a difference. Like if we took a pipe on one side of our 4th floor of that Voorhees building, and we dropped it 1/4 of an inch per foot and ran that pipe all the way across to the other side of the building, there'd be a substantial drop there because that's several hundred feet of distance. So that'd be several feet of drop. And what I'm pointing out is, if you think about it, it's very possible that if you started the pipe in the ceiling cavity, which is the distance between the drop ceiling, the WC, the acoustical tile, and the actual ceiling above, or the bottom of the floor of the next floor above, if you started at the highest point where the pipe just starts touching that concrete floor above, and we let that pipe drop at 1/4 inch per foot, it would be well below the ceiling on the other side of the building. So that's very important to pay.
Professor,
Yes.
someone's in the waiting room.
Oh, I don't see that. Okay, but thank you for telling me. Let's see if I can accommodate them. Oh yeah, several people in there. Thank you for telling me that. I didn't see that. All right, I think everybody's here now. So anyway, the important thing is to pay attention and recognize that at 1/4 inch per foot over a long span, you're going to find that starts maybe in the ceiling space and it ends up well below the ceiling space, which could be an issue. So that's always a concern, an embarrassment too, if you haven't accommodated for that. You could have in our corner room there in the Voorhees building on the 4th floor, we could have, if pipes were traversing the long axis of that building, there would be, those pipes would be visible, and we might be so low that we couldn't walk underneath them. We'd have to duck down. So that could be an embarrassment, but we want to use gravity to take that water away, and 1/4 inch per foot accommodates that issue. So we have some different kind of materials that we would use for drainage. Now, drainage is different than supply. Remember, we're talking about getting the water away. So that water is already contaminated. It has the dirt from our hands that we washed off, and from our dishes and our bodies when we take a shower or a bath. And of course, the water from the toilet, that's all not potable water by any means, and it's not something that we would drink. But we want to put that in certain types of pipes with certain types of materials so that it would allow that water to go away. So cast iron is very common. Cast iron is a good material in a vertical wall, because it's has a very good sound transmission coefficient, meaning that it doesn't allow the sound of the water to be heard. So if you're in this house on the second floor and you flush a toilet, the water's going to flow down a pipe through the walls. And if you're in a room on the first floor where that pipe is having water flow through it, if it's cast iron pipe, you're probably not going to hear that water flow through it. If it's plastic pipe, there's a good possibility that you're going to hear that water flow through that pipe. Cast iron is very expensive, and it's much more difficult to connect the pieces than plastic is. So in your new construction, certainly your apartment buildings, you're most likely to see some sort of a plastic in the wall rather than a cast iron. But the result of that is that if you're in an apartment on one floor and the people above you are flushing their toilet, it's going into a pipe, and you might be able to hear that. So we do use different materials, but it's very expensive for cast iron, and so it's being used less and less. But if you look at the drainage pipes in the subway, you see them coming down at the different columns. They're cast iron pipe. The city did it right, but it was probably a factor that one of the reasons that they're using cast iron there was because it was a long time ago that they put those pipes in. The advantage is that they'll last very much a long time. And does it really matter if we can hear the water coming through the pipes in the subway system? I don't think it does. But plastics are more and more common for drainage. There are places where we can use plastic for the supply lines, but we talked about the outgassing of the chemicals in the plastic pipe into our water system, which we try to avoid if it's all possible. I don't see vitrified clay pipe being used in any way, shape, or form today, but we might see galvanized steel, stainless steel, or copper also being used. Copper's expensive. Stainless steel is even more expensive. If the pipe is going through an environment that's very hazardous, then you might justify putting in stainless steel, but otherwise it would be very hard. You'd be very hard pressed to be able to defend your decision to the client, to the owner, to the contractor, to a judge, to a jury, to a mediator, to an arbitrator, that you specified stainless steel in a project because it's very, very expensive. Unless it's going through a hazardous environment, it's on the outside of the pipe, it's probably not a defensible material. So here's when we talk about a trap, we were talking a few slides earlier, we were talking about a trap. And this is what it looks like. It is an object right here in the sink. It's got this U shape to it. And the water that stays in this trap is used to what? To not allow the foul gases that are inside of the pipes to get back into the facility. So if this water wasn't here, then those foul gases would be able to come back and into the facility. So laundry room, for example, I had a client that I designed a house for, and he wanted two laundry rooms in his house, one next to the other. Now, I have used this example many times in this class. I never asked him why he wanted two laundry rooms in his house. But being the good architect that I am, in the back hall of his house, we put two laundry rooms with washers and dryers, and laundry tub, sinks, cabinets, countertops, folding area. It was very nice. When he moved into his house, he called me one day and he said, Bob, I think the contractor has made a mistake because one of our laundry rooms smells really, really bad. He said, we don't use it, but it smells really, really bad. And I think the contractor has done something wrong. And if I have successfully explained the purpose of a trap to you, I'm going to pause here and ask somebody to suggest to me and to the class, um, with the facts that I just gave you, why did the laundry room that the family did not use stink? Why did it smell? Somebody out there is a good detective and was paying attention to what I said, and they would be able to answer that question.
Wouldn't it be because of the foul gases? Or maybe there's like no P trap?
There was foul gases, and there was a trap put into his system, but you're on the right direction. There's just an element that's missing. Um, there was a byproduct of the fact that he did not use that room.
Oh, okay.
Being used, so the gases weren't being flushed out.
Well, if he's not using the room, then he's not using the sink. If he's not using the sink, then the water seal that would normally be created by pouring water into the sink, all of this water evaporated. As soon as that water evaporated, that allowed the gases to come back into his laundry room, his unused laundry room. And so my solution to him, without having even gone out to investigate if there was in fact a trap there, but my solution to him, I thought, was very simple. What do you think I told my client to do in the laundry room that they did not use?
Faucet on?
Exactly. To go into that laundry room where the water had been able to evaporate from the trap, which was the reason that gases were coming back into the space. Simply turn the water on and it would fill up this point right here with water, which would create a natural blockage or seal, which would prevent the gases from coming back into the space, which is exactly what he did, and which is exactly what solved his problem. Now, it's a fair question to ask, and I did not. Why do you need two laundry rooms and one of them you don't even use? So the focus in this class is the fact that the water wasn't there. But the question that I've always had, and if I ever talk to this client again, he's probably already sold that house and moved on, but maybe not. I would ask him, if I see the contractor again, I would ask the contractor if he remembers that client and why. I just haven't run into either one of those people, but it's a question that I'm sure I would like to know the answer, and maybe there's some other people too. But that's the solution. That's the exactly what correctly was wrong and was easy to correct was there was no water in the trap. And by turning the faucet on, it created a water seal, which stopped the gases from coming back into the house. So this is part of your requirement for your final project is to draw the riser diagram for that house. So we would simply, it's a schematic diagram. It's not an actual to scale physical three-dimensional drawing. It's a two-dimensional drawing which simply shows we draw three lines to represent the floors. And then inside of each of those floors, we simply draw rectangles, which are fine. You could be more accurate and draw the actual symbol of a toilet and the symbol of a sink and the symbol of a tub. But that is not necessary for this class. But you need to extract from the plans how many tubs, how many lavatories, how many water closets, how many showers are on this floor and draw the rectangles to represent those. So each bathroom can have those. And if there was another bathroom, you might put the same thing here, tub, lavatory, and water closet again over here. Or you might put a tub, lavatory, and water closet and shower over here on this side. But it's a graphic representation of how the fixtures in the facility that I've given you the floor plans for, how we're going to drain that. And basically, we're going to connect these objects to a pipe, and we're going to tell, based upon this, what the size of that pipe is. So here we have a water closet. It needs a drain and a trap. Now, a water closet, the trap is built into the device. So we don't need to specify that, but we do need to specify what the size of the drain is. So from that water closet, you highlight this right here and say that is what? From a water closet. We go back over here, water closet's going to be 3 inches or 4 inches. Okay. And we're going to label all of those like Dr. Edwards has done here. He's put a few labels on there to show you what that needs to be. Now, this pipe needs to be 2 inches. Why? Because the tub is 2 inches. But when we get over to here, it needs to be 4 inches. Why? Because the drain pipe from the water closet is 4 inches. Okay. So we always want this pipe here, which is collecting all of the gray water or black water from these fixtures. It has to be at least the size of the so it makes sense that if this were a 4-inch pipe and this were a 2-inch pipe, then you'd have a problem with the flow of the water. So it's always got to be as big. So if the water closet were over here, then this whole pipe would have to be 4 inches, if that makes sense. And that's how we would represent that. It doesn't have to be a beautiful graphic diagram, but we want to show what is going on with the drainage. And then we want to show how we're venting our fixtures to get those sewer gases away from the fixture. So each fixture can have its own vent pipe, or each fixture can be connected to a vent pipe, or this method, just the farthest away fixture can be connected to a vent pipe. All right. So this is a continuous venting, means that every single fixture is connected to that vent pipe. And Circuit venting means that the farthest fixture away is connected to that vent pipe. So this fixture is not connected to the vent pipe. It's got a drain, but it's not connected to the vent pipe. So that would be circuit venting, an example of circuit venting where somewhere else there is the fixture that is vented, or continuous venting where every single fixture is vented, connected to the vent pipe. So this is the diagram that eventually you'll take the information from the architectural plans and extract them in a graphic visual form, very similar to this, which would be fine. But on the first floor, I think we have a powder room. Yep, so you're gonna have to have a water closet. We might not have a bathroom or bedroom we might not have a bathroom that has a tub, so we might get rid of the tub on that. But we do have a sink in the laundry room. This might be very close to we have a sink in the kitchen too, so we would put another sink there for the kitchen. Those are the things that we want to integrate into our riser diagram. This is a good example, but of course there's many, many great examples on YouTube that will explain riser diagrams, but this is a good example. If you need reference, just go to YouTube or go to the internet and ask for some examples of riser diagrams. There'll be quite a few different examples to look at.
A question?
Yes.
Is there any reason not to use what's it called, circuit venting like more often than continuous, since it would use less material?
Well, you're definitely right. You would use less materials with circuit venting, but not continuous venting. But my argument would be to always use continuous venting, because what if for some reason this vent fails? Now you have no vent at all for any for this space, for this room. Whereas if this one fails, you still have venting for the other fixtures here. So that would be my argument to do it. However, there are municipalities that will allow circuit venting. If you're really doing this for a real project, you would definitely want to make sure what the municipality's position is. If I were the person in charge of any municipality, I would not allow circuit venting because of the failure. If this fails, then you have no vent left anymore. I would always insist upon that, and I suspect that most municipalities will require continuous venting, not circuit venting. But you're right, you said you save a lot of money on materials, not only materials, but you save money on labor too. There's a plumber that's connecting these. His kids need braces too. He's not working for free. Or they have kids in college like you guys, and you know, he might or she might or they might need to pay their anyway. The point is that they're not doing it for free. You're going to pay for it. So there's not just materials, but there's labor too. So some people might want to take a shortcut. I wouldn't advise it. I don't see the advantage in the long term other than material and labor costs. And the reality is, for the most part, when you're building a house, you're not paying for it. The people are usually not paying for the house in cash. They're getting a mortgage and they're paying the house off gradually in small amounts. So the difference in cost, say, is $1,000 between, I'm just throwing out a number there. Say the difference in continuous venting versus circuit venting, it's an additional, for continuous venting, it's an additional $1,000. Your house gets paid off over 15 years, 20 years, 30 years. There's even longer mortgages now. So the cost of that $1,000 amortized over 30 years is not a whole lot of money, really. Plus, there's the depreciating cost of the dollar. So that $1,000 that you paid today and with your mortgage money, you're gonna pay back with money that's worth less and less and less. So you might be making $100,000 a year today to be able to pay your mortgage. Your mortgage stays the same, the price does. The cost of the mortgage every month, your payment is the same generally, unless you have a fixed rate mortgage. But your income increases so that 5 years from now, you're making 150, 10 years from now, you're making 200,000. The purchasing value of that 200,000 is the same because of inflation as it was 10 years earlier at $100,000 of income. But your mortgage payment stays the same, and now you're making twice as much money or 3 times as much money. So yes, more cost, yes, more labor, amortized over 30 years with the depreciation value of that dollar because of inflation. It's silly not to do that, because what happens if you have a failure here? Now you have to bring a plumber back in to unplug or unclog that or fix that vent. And that's not that person has kids too, has that need braces, college education, food, fancy shoes, and on and on and on. So the point is, they're not going to do it for free. You're going to pay for it. So it's much cheaper to do it correctly the first time, especially if you're planning on living in that house for a long time. We've lived here in our house for 35 years now. And I don't think when I built the house, I don't think I had any anticipation of living here this long, but it's working out so well for us that there's no reason to go anywhere else. So some people are going to stay that long, 30, 40 years in their house, and other people, it might not make sense if you're only going to stay there for a year and you have the choice of saving that money or not. Might, probably not going to fail in the first year. But it's still labor and materials here, but it's insurance as well to make sure that your fixtures are vented. So what do we have? Well, we have the trap, we have the vent stack, we have the soil stack, the stack vent, the soil lines, the waste line, the drain pipes, the sewer pipe, the continuous venting, and the circuit venting. So let's go back. Where's the trap? Right there. That's this guy. This is the trap. It's not made to trap particulates like your food waste or things like that. Or mud from your hands as you're washing them. It's made to trap the foul gases from getting back into the house. So that's our trap. We have our vent stack. That's right here. That's our vent stack right there, which our soil stack taps into. Okay, right before it penetrates the house at the roof line, it'll tap right into that vent stack. Okay, it's a vertical pipe. The vent stack is a vertical pipe, goes through the floors and through the roof, and it does connect the horizontal vent lines from the plumbing fixtures. Okay, so that's the vent stack, and it connects the horizontal pipes to the fixture from the fixture. The soil stack is, again, the vertical soil pipe, goes through the floors, connects the horizontal drain lines from the fixtures. So that's connecting these from the fixtures. That's our soil stack. So the soil line would be this guy. This is our soil line. These are our soil lines. Okay, soil lines that connect that. And the waste line, interesting. The soil line is pipe carrying waste from water closets and urinals. Okay. And the waste line is carrying anything but soil. All right. So the waste line carries the discarded water from the sinks. The soil line carries them from the water closets and the urinals. Okay. So that's the really bad water. Then the drain pipe. We have a drain pipe over here. Outside of the building, this is the building edge. Then we have a sewer pipe, which is waste pipe that connects to the public sewer about 3 feet away from the building edge. We have that it transfers to the a building from the building sewer to the public sewer. And then we talked about continuous and circuit venting. So for the vents, we want pipe size. What do we want? Well, not smaller than a half-inch, not smaller than half the diameter of the drain pipe served. What does that mean? So this is 4 inches. So we want our vent pipe to be at 4 inches. We want our vent pipe to be what? 2 inches, half, not less than half the size. And in no case should they be less than 1.25 inches in diameter. Okay, so our vent pipes should not be less than half the size of the pipe or 1.25 inches at a minimum. All right, so we have two different types of drainage. We have the storm drainage, which is the water that drains away from the buildings and the ground. And then we have the sanitary drainage, which is the water that drains away from where? From our fixtures inside of the building. All right, that's the sanitary. And we ideally, and in most municipalities, those are two entirely separate entities. But Manhattan and Brooklyn are so old that they have combined their system into one. And so the storm drainage, which is the runoff from the roofs of the buildings to the sidewalks to the roads, are storm drainage. The sanitary drainage comes from the fixtures and drains inside of the building. We try to keep those separated, but in the case of Manhattan and Brooklyn, you haven't because they're so old. So what does happen is when we have a torrential rain, the storm drainage system, which is also the sanitary drainage system, can't handle all of the water that's being flowed. And that water is going to try to find a place to go to. And if you have a connection to that sewer system and you have it overflowing, it's going to find its least point of resistance. And so that is a good place to have one of these, a check valve, okay? So that the sewage can drain out this way, but when there's pressure coming in the other direction and it's trying to bring it back into your building, because the sewage and the rainwater are connected together, are all in the same space, and it's too much. We want that check valve to stop the sewage from coming back into our facility. But what also happens, of course, is that coupling the storm drainage with the sanitary drainage, that all of that goes to a treatment plant, is directed to a treatment plant. And when we have those torrential rains, the treatment plant is not capable of handling that large volume of water. So they divert much of it right into the Hudson River. So it's not uncommon during a heavy rainstorm for Manhattan and Brooklyn to dump 50 million gallons of raw sewage into the Hudson River. Fortunately, the Hudson River is an outlet, and we're close to an outlet that dumps that water into the ocean, so which dilutes the sewage, but it's still not a healthy or smart thing to do. But the system isn't designed to carry the large volumes of water that occasionally occur. And so it has to be diverted somewhere, and that's going to be diverted right into the Hudson River. So I see every once in a while I see on the news that 50 million gallons of raw sewage was dumped into the Hudson River. Not a good place to swim for sure. Um, Anywhere around us in the Hudson River. It's not clean water at all. So what do we have cleanouts for? Well, let's go back and take a look where we're showing cleanouts. Dr. Edwards is showing cleanouts here at the high point and the end of the drain. And that would make sense if we put the cleanouts here. And what the cleanout is made to do is to allow somebody to get into the pipe system and unblock some sort of blockage that might be clogged for whatever reason. Now, if you think about it, this is your house and your cleanout is down here and the plumber shows up to open up that cleanout and unclog some portion of this pipeline up there. When they unclog it, that water is going to drain down, and with that cleanout still open, it's going to all of that sewage is going to come into your house. So it does make sense to have the cleanouts where at the high point. If he or she unclogs the pipe now, it's going to naturally drain by gravity, not in this direction, but rather in that direction. So we want them at the ends of lines. We want them at intervals in the pipe, and certainly at the foot of the soil stack. Foot of the soil stack. We want to clean out where there's a 45-degree turn or greater. So 45 is a substantial turn, but it's possible for something to get clogged at that point. So we would like to have a clean out wherever we have a 45-degree turn of the pipe, and certainly within 3 feet of the building line. So we have a clean out right there at within 3 feet of the building line. So if it gets clogged here, if the pipe gets clogged here somewhere, we can go in and clean it out so that it can continue and go to the municipal sewer system. So if you walk around Manhattan, you will see maybe tripped over, stepped on, walked on, of course, access points for the public sewers to get in there and do general maintenance and inspect it. And about, if you were to walk them off, you would see that if you were measuring your paces, you would see that we're looking at about 150-foot intervals where you would see that. Now, interceptors, we put interceptors to catch oil and grease, hair, food particles. Absolutely have to do that in restaurants because they get a lot of grease and food particles. So we have to intercept that before it goes into the public waterways, the municipal connectors. But we also do that if we have to put a lot of my clients heat their garages. So when they pull their car in with snow on it, the snow melts away, and we have to drain that away from the garage. So there also we have to put interceptors because the cars also not I'm contradicting myself here because my clients' cars don't, they're expensive and new cars. They generally don't leak oil and things like that, but we have to plan for that possibility. So the drains in garages are connected to interceptors as well, which will collect oil, grease, and whatever else might come in from the garage from the car itself. So the water ends up being where? At a public treatment plant. Remember, for some reason, we have decided that we can do a better job of treating the water than nature can. We only have a short couple of thousand years worth of history of doing it, where nature has been successfully doing it for billions or more years. But for some reason, we've decided that public treatment plants are the proper way to take care of things. And so that's where, first of all, the solids and liquids are separated. And the liquids sometimes are oxidized. And then we have the clear water and we chlorinate that. We let the solids settle out of the water, and we get here we're letting nature, the anaerobic digesters, the bacteria actually consume a lot of that solids that come out of the water. And then we take the rest of that and we use it for fertilizer or for landfill. A lot of New Jersey is landfill of these very materials, and the byproduct of that is a lot of people living on top of really bad chemical outgassing. So there has to be a lot of sealing of the basement so that those gases can't get into the buildings, into the facilities. But we take some of that and we use it for fertilizer. It's a very good fertilizer because that's part of the natural cycle of things, that circular thing, and we're just sort of short-circuiting it and then going back to the fertilizing, using it for fertilizer again. So here's a system where we don't have the availability to connect to a public sewage system. So when I was driving around looking for property to buy to build this house or our next house, I looked at several parcels of land in various cities, and this was the piece of property that I ended up purchasing. Is this the one that we live on now? And it was a beautiful natural site, southern sloping, which is important to me as an architect because you want the building to have a southern exposure. And it was on a lake, and it was very, very reasonably priced. It was substantially lower than another piece of property in this same neighborhood. Substantially, to tremendously substantially lower, to the point where it was ridiculously inexpensive for a lakefront property in affluent suburban setting. But I ended up buying it anyway because I thought the seller had no idea what the value of their property was. But it turns out that the seller did have a pretty good understanding of what the value of that property was, because after I purchased the property and I drew the architectural plans to build the house, and I took those plans to the city to get a building permit, they told me that the piece of property that I had purchased was unbuildable. In other words, I could not build a house on that piece of property, which explained to me why I was able to purchase this piece of property so cheaply. And the reason that it was unbuildable is that this particular development did not have public sewers in it. And the city, wisely, I will admit, had said that no lakefront properties can have sanitary systems like we're looking at right now. This is a private sewage system. It's a septic tank, because of the fear that some of this water from the septic tank would leak or leach into the lake. So I was faced with an absolutely spectacular piece of property on a beautiful lake in the beautiful suburb that I could not build a house on. because there was no public sewer. I expected, because I was a young pup, not too smart in the ways of the world, I guess, because I didn't pay attention to whether there was a sewer or not. I just looked at this beautiful piece of property and said, wow, it's a good price. I'm going to take it. You never want to sell anything to me because that means that you're selling it at a lower than market value. And you never want to buy anything from me because that means you're buying it at a higher than market value. And so I saw something that I felt was priced much less than its actual value, which didn't turn out to be true. So what I had to do in order to build my house here was I had to have the public sewers put into this development, which was a very expensive endeavor. But it wasn't, I didn't have to pay for all of it. I only had to pay for a portion of it. And then I forced my neighbors to pay for their fair share of it. And so obviously when I first moved into the neighborhood, I wasn't very popular. But I thought I was going to be able to do a private sewage system because there wasn't a public system. And it turned out that I couldn't because this municipality that I live in does not allow it. And I think that's the smart move. So we had to put the sewer system in. But if this is what I thought we would be able to do, was to have a septic tank which separates the fluids and the liquids. This is where all of your wastewater comes in from the house instead of connecting to a municipal system. You build a septic tank system. And so what happens first of all is all the sewage comes into here. And then we get some of that reduction in the volume, again, by anaerobic digestion. That's nature taking care of it, bacteria going in and eating that stuff. But every couple of years, more or less, depending on how many people actually live in the house, it has to come out, and there's a truck that comes and sucks all of that sludge out of your septic tank. But the remainder of it travels through and then goes out, and we use nature again to filter the water. And that's not a really good system for places that have public water access on it. It didn't turn out to be a very good idea. So we take a different look at it here. What you're seeing is, there's the house, and you go into the septic tank itself, and then the water comes out, and it is distributed along long pipes where it filters, where it seeps into the ground, and the ground filters it out so that by the time it gets to the groundwater, that it's clean water again. All of the contaminants are back into the soil. But if this is a lake and this fails, then the sewage is just being dumped right into the lake. Now, in the Hudson River, you guys have decided that that's okay to dump your sewage into the Hudson River. But here in my suburban town, when on our waterway, on our lake here, we have determined that that's not a good idea. We don't have a tidal system where the water goes out, and clean water comes back in, and dirty water goes out, and clean water comes back in. So, but that is the septic system. So if I had purchased this property and I was not an architect, and I had a company come out and do a soil analysis where they actually dig test samples into the ground, they drill into the ground and pull out the soil and determine what the bearing capacity is, and what the material composition is, that they would be able to tell if it was porous soil or semi-porous soil or non-porous soil. Okay. And what that means is, for porous soil, the water can percolate through it. Semi-porous is the water can percolate through some of it. And for impervious soils or non-pervious soils, that means that the water can't percolate through that. And we're talking about earth materials like clay. Water doesn't percolate through clay, doesn't clean it out. So anyway, if we tested it, and the results came back that it was porous soil, then we would use a cesspool. Okay. If the results came back and it was semi-porous soils, then we would use a leaching field. Okay. And if the test came back where it was impervious soil, then you would have to take that soil away and replace it with pervious soil, sand, and build a engineered septic field, which is very, very expensive to do. So I think there are some questions on not this current quiz that you'll be taking that's open now and closes at 10 o'clock next Friday. But on the coming up midterm for sure, that I'm going to tell you I have a porous soil. What type of sanitary system should I put in? And your answer would be cesspool. And if I said I have semi-porous soil, what type of system should be put in? Your answer would be leach field. And if I have a need for a sand filter, what kind of soil does that mean that I have? And the answer would be it's impervious soil. Those are the things that we have there. So we have reached a very comfortable point to stop at, which cleverly is comfort is the next topic, which is thermal comfort. And we do have a unit called BTU, British Thermal Unit, and we do have a definition of what a British thermal unit is. Whereas a fixture unit, we don't have a definition that defines a mathematical formula that defines what a fixture unit is. And we do have one for BTUs, and we'll talk about that because thermal comfort is very important to us. But I'm going to take attendance now or finish taking attendance, and then we'll see if there's any questions, comments, thoughts that anybody has. And after that, we'll call it a day. So I'm looking for, I'm using the attendance from the actual Zoom that I can see who's here. I'm going to go through and just do that, use that, and then if there's anybody that's not here that I missed, maybe I'll call it out. So sit tight with me for just a moment. And if you're gonna, now would be a good time to think about any questions that you might have or any thoughts or comments that you might have.
Professor,
Yes,
next week is in person?
yes,
Okay.
good question, definitely.
A question. This class is gonna be uploaded?
Yes, it has been recorded and I will upload it later today at the earliest and tomorrow at the latest.
Professor, the quiz that I see open is called Quiz 1 Water Supply and Thermal Comfort. Is that the one that we're supposed to be taking?
Um, no, it's just water supply. So it should just have water supply questions on it. I did make one with water supply and thermal comfort, and then I realized that we haven't done the thermal comfort yet, so I couldn't ask you those questions. Now I've got a student here, M. IA. I don't know who that is. Can you help me out there?
Mia.
Oh, Mia. Okay.
Mhm.
Thank you, Mia.
Sorry, Professor, can you go back to the previous slide?
That would be this one.
Yes, thank you.
All right. So I do not have Stephen Taylor, and I do not have Saqib Hussain. Are you here, Saqib? And Jaden Hernandez, are you here? Don't see you. And everybody else is here. So everybody else is marked here. All right, so let me go now. Let me do that. Make sure I got the right quiz up there. Yep, that's the right one. So it really should just say water supply.
It says it's due April 3rd, but is that just error?
That's a big error, isn't it? Yeah, let's fix that now too. It should be March 3rd, or let's see. So it should be March 6th, I'm thinking, huh? Yeah. Yeah. That's better. March 6th. Yeah, that's much better. All right. So what other questions,
Professor,
thoughts? Yes.
Professor, what's the duration of the quiz?
How much time do you have to take it?
Yes.
I believe you have, well, I think you have to take it all at one sitting. I might not have set it to do that. It's only 10 questions, but it's
Okay.
due next Friday at 10 o'clock.
Thank you.
Okay.
So you last week you had said something about calculating the area using Revit. If possible, could you like show that?
Using Revit for what?
To calculate the area.
Oh, yes. Um, I don't think I've posted the Revit model, I can load that. I'm gonna make a note to make sure I do it. I'll load the Revit model for this, so those of you who have any Revit capabilities, can use Revit. All right, I made a note, so I'll make sure to get it done. So let's take a look at, can you see my Revit screen now?
Yeah.
Yes, Professor.
Yeah.
Okay, so I'm gonna go to an elevation. Like this one. So I know this is the area that I want to calculate. Okay, let's do this one. So this is your so if I know that's the area I want to calculate, I can draw a annotate region, and then I can just draw a region from where to where I think it should be. And then if I click on that region, it tells me in the properties what the area is, 182.67 square feet. So I can use Revit. $182.67. So that's how I would use Revit in order to calculate the square footages. So same thing, I already put the area over here. I just click on it and it is 228.33 square feet. So I can write that down. And this should be that blue, so I'll just change the color to blue. Yeah. So I'm just changing the properties of that color of that region to whatever color I want it to be. Does that make sense on how to do it?
So did you just
Yeah.
click on it, Professor? Did you just click on the wall and then
I-
it gave you the area?
I clicked on this region. So I made a region, and then I made a rectangle and I just made a region, whatever size I want it to be. And then after I've made that region, when I click on it, Revit will tell me what the area, see over here, it'll tell me what the area of that region is. So that's calculating. The other way to do it is to know what the horizontal distance is, what the vertical distance is. So say 23 feet by 8 feet. 23 by 8 is what? 23 times 8.
184.
Yeah, but it's only 22 foot. So Revit's doing the precise dimension of 22 foot, 10 inches by 8 feet. So 22 feet, 10 inches times 8 feet equals 182.67 square feet. Yeah, so that's the exact calculation, but we can round that up to make the math easier. We just say 8 by 23. Does that make sense?
Yeah.
Yes, yes.
All right. I'll see everybody next week at campus. It's in person.
Thank you, Professor.